October 29, 2025, a Manhattan-sized object from beyond our solar system reaches its closest point to the Sun, hidden from Earth's view by our own star's blinding glare. For 8 days, the world's telescopes sit blind. But behind the Sun, something impossible happens. Data streams in from orbiting satellites positioned where Earth cannot see. The numbers don't lie. The interstellar visitor designated 3I Atlas has just done something that gravity alone cannot explain. A NASA engineer at the Jet Propulsion Laboratory files a report that changes everything. The object has accelerated, not from the Sun's gravity, not from any known natural force. It moved on its own, and when it emerges from behind our star, it's no longer the colour it was when it went in. This is the moment we've been waiting for since July 1st, when humanity discovered its third confirmed visitor from the depths of space. This is the confirmation that 3I Atlas is unlike anything we've ever seen. The question is no longer whether something strange is happening. The question is what happens next. The data came from Davide Farnocchia, a navigation engineer at NASA's Jet Propulsion Laboratory in Pasadena, California. Farnocchia earned his PhD in mathematics from the Galileo Galilei School of Graduate Studies at the University of Pisa in Italy, and he specialises in tracking small objects through space, calculating their trajectories with extraordinary precision. His work focuses on detecting non-gravitational perturbations, those subtle deviations from purely gravitational motion that tell us when something else is at play. He's the person you call when you need to know if an object is following the laws of physics or breaking them. On October 29, 2025, at approximately 11:47 Universal Time Coordinated, 3I Atlas reached perihelion, the closest point in its trajectory to the Sun. The object sat at a distance of 1.356 astronomical units from our star, which translates to roughly 203 million kilometers or 126 million miles. That's between the orbits of Earth and Mars, close enough to feel significant solar heating but far enough to remain relatively safe from the most intense radiation. For weeks, astronomers had been counting down to this moment, knowing it would be the acid test of the object's true nature. If 3I Atlas was simply a natural comet, perihelion would trigger massive outgassing as frozen volatiles sublimated under solar heat. If it was something else, something engineered, this would be the moment when it might reveal itself through maneuvers, transmissions, or other technological signatures. But there was a problem. Earth couldn't watch. 8 days before perihelion, on October 21st, 3I Atlas entered solar conjunction, positioning itself directly behind the Sun as viewed from Earth. The solar elongation dropped below 15 degrees, well below the threshold for ground-based optical telescopes. The Sun's overwhelming glare made direct observation impossible for more than 2 weeks, from October 8th through late October. Earth's most powerful observatories sat idle, unable to track the most important interstellar visitor in human history during its most critical phase. It was a blackout window that seemed almost designed to keep us in the dark. Almost. While Earth-based telescopes went blind, a handful of spacecraft remained in position to observe. The Solar and Heliospheric Observatory, known as a SOHO, orbits the Sun at the first Lagrange point between Earth and our star. The Solar Terrestrial Relations Observatory, called STEREO, consists of 2 spacecraft that monitor the Sun from different vantage points, and the GOES-19 weather satellite, though designed for terrestrial meteorology, has instruments capable of detecting bright objects near the Sun. These platforms, positioned away from Earth's line of sight, could see what we could not. Throughout the blackout period, they kept watching, and what they saw didn't match the predictions. Data from the Atacama Large Millimeter Array provided the smoking gun. ALMA is one of the most powerful radio telescope arrays on Earth, capable of detecting millimeter and sub-millimeter wavelengths with extraordinary precision. On October 29th, ALMA locked onto 3I Atlas as it passed through perihelion and measured its position relative to its predicted gravitational trajectory. The object was 4 arc-seconds away in right ascension from where it was supposed to be. 4 arc-seconds might not sound like much. It's roughly the angular size of a basketball held at arm's length when viewed from a mile away. But in orbital mechanics, it's enormous. It meant that 3I Atlas had deviated from a purely gravitational path. Something was pushing it. Something was changing its course. Farnocchia's report, filed through official NASA channels, quantified the deviation with two distinct components. The first was a radial acceleration, a push directed away from the Sun, measuring 135 kilometers per day squared. To put that in perspective, that's equivalent to approximately 9 times 10 to the negative 7th astronomical units per day squared. The second component was a transverse acceleration, perpendicular to the radial direction relative to the Sun, measuring 60 kilometers per day squared, or about 4 times 10 to the negative 7th astronomical units per day squared. These weren't random fluctuations or measurement errors. They were consistent directional forces acting on the object in its orbital plane, forces that couldn't be explained by the Sun's gravity, by radiation pressure, or by any other purely environmental factor. The magnitude of these accelerations corresponded to a spatial deviation on the order of 10 times the radius of Earth over the course of a month. That's not enough to bring 3I Atlas significantly closer to any solar system planet from its original trajectory, but it's more than enough to rule out measurement error. The detection stood at a statistical significance of 3.7 standard deviations, well above the threshold for scientific confidence. This wasn't noise in the data, this was real. Now comes the question that divides the astronomical community into two camps. If 3I Atlas is accelerating in ways that gravity cannot explain, what's causing it? The conventional answer, the one favoured by most scientists, is outgassing. Comets are made of ice and rock, frozen volatiles that sublime directly from solid to gas when heated by the Sun. As these gases escape from the nucleus, they create thrust, a rocket effect that can alter the object's trajectory. We've seen this countless times in short-period comets from our own Oort cloud. The jets are visible, the plumes are detectable, and the resulting accelerations match the observed mass loss. It's textbook cometary physics. But 3I Atlas isn't following the textbook. To produce the level of acceleration Finokia measured, momentum conservation requires a staggering amount of mass loss. Harvard astrophysicist Avi Loeb, director of the Institute for Theory and Computation, ran the calculations as soon as the data came through. If the acceleration is driven by gas ejection, and assuming an ejection speed of a few hundred meters per second, typical for thermal sublimation, then 3I Atlas would need to lose approximately 10 to 16% of its total mass during its month-long transit through the perihelion region. That's not a gentle puff of vapor, that's catastrophic evaporation. The numbers get even more extreme when you factor in the object's estimated mass. Earlier observations between May and September 2025, compiled from more than 4,000 data points from 227 observatories worldwide, showed that 3I Atlas had almost no measurable non-gravitational acceleration during those months. The upper limit was about 15 meters per day squared, far below what's now being detected. Given the known mass loss rate measured by the James Webb Space Telescope in August, around 150 kilograms per second, this lack of detectable thrust implied that 3I Atlas must be extraordinarily massive, at least 33 billion tons. At solid density, that corresponds to a minimum diameter of about 5 kilometers, roughly the size of Manhattan. If an object that massive lost 10 to 16% of its mass in a month, the result would be a debris cloud exceeding 5 billion tons of gas and dust. That's a plume so large it would dwarf anything ever observed from a comet. It should be visible from hundreds of millions of kilometers away, glowing brilliantly as sunlight scatters off the particles. When 3I Atlas emerges from behind the Sun in late November and reaches its closest approach to Earth on December 19, 2025, at a distance of 269 million kilometers, hundreds of ground-based telescopes will be pointed at it. The Hubble Space Telescope and the James Webb Space Telescope will conduct detailed spectroscopy. If the massive gas cloud is there, we'll see it. If it's not, then the acceleration cannot be explained by natural outgassing. And that opens the door to something far more extraordinary. There's another anomaly that complicates the picture even further. As 3I Atlas approached perihelion, its appearance changed in a way that defies conventional comet behavior. Observations from the Stereo, SOHO, and GOES-19 satellites revealed that the object brightened rapidly, far more rapidly than typical Oort cloud comets at similar distances. The brightness scaled inversely with distance from the Sun to the power of negative 7.5, plus or minus 1. That's an incredibly steep gradient, suggesting either unprecedented levels of volatile sublimation or something else entirely. But the real shocker was the colour. Earlier observations in July and August 2025 had shown 3 Atlas with a reddish hue, consistent with dust-scattering sunlight. That's normal for comets. Dust particles scatter shorter blue wavelengths more effectively than longer red wavelengths, giving comets their characteristic ruddy appearance. But as 3 Atlas reached perihelion, it changed. Colour photometry from the spacecraft observing near the Sun showed the object becoming distinctly bluer than the Sun itself. Not just less red, not neutral. Blue. Intensely blue. This is, to put it mildly, very surprising. The surface temperature of 3I Atlas at perihelion, based on its distance from the Sun, should be around 20 times colder than the solar photosphere, which sits at 5800 degrees Kelvin. Colder objects emit redder light. That's basic blackbody radiation. Dust scattering makes things even redder. For 3 Atlas to appear bluer than the Sun, something had to be generating light at temperatures comparable to or exceeding solar surface conditions. There are only 2 plausible natural explanations. One is ionized carbon monoxide, which can emit blue light under certain conditions. The other is that we're misinterpreting the spectroscopy. But neither of those explanations fully accounts for the observed intensity and colour profile. The alternative explanation is technological. A hot engine could produce the blue glow. Artificial lighting, whether from internal power sources or plasma exhaust, could create the observed signature. If 3I Atlas is propelling itself using some form of advanced propulsion system, one capable of generating the observed accelerations while expelling superheated plasma, then the blue colour makes perfect sense. It's the exhaust signature, it's the evidence of active thrust. A.V. Loeb has been careful not to overstate the case. In multiple public statements and scientific papers, he acknowledges that natural explanations remain plausible. But he also argues, rightly, that scientific truth is not decided by popularity or authority, it's decided by data. And the data, so far, does not conclusively favour either interpretation. The blue colour could be ionized carbon monoxide, or it could be an engine. The non-gravitational acceleration could be country evaporation, or it could be technological propulsion. The only way to know is to look for the gas cloud. If we observe 3I Atlas in November and December 2025 and find a massive plume of gas surrounding it, carrying billions of tons of sublimated material, then the natural explanation wins. The object is an interstellar comet, albeit an extraordinarily large and active one. But if we don't see the cloud, if the object emerges from perihelion without the expected debris field, then we're facing something unprecedented. We're facing the possibility that 3I Atlas has a propulsion system. This isn't the first time we've encountered this dilemma. In 2017, Oumuamua became the first confirmed interstellar object to pass through our solar system. It displayed a measurable non-gravitational acceleration as it swung around the Sun and headed back into deep space. Astronomers searched for cometary outgassing, using the most sensitive instruments available, including the Spitzer Space Telescope. They found nothing. No gas, no dust, no tail. The acceleration was real, confirmed by multiple observatories, but the mechanism remained unexplained. Comet experts eventually coined the term dark comet to describe objects that show non-gravitational acceleration without visible cometary activity. It's a term that raises more questions than it answers. If a comet's defining feature is its tail, then what exactly is a comet without a tail? The phrase is almost an oxymoron, like calling something a dark light or a silent sound. Now we're seeing history repeat itself, or at least rhyme. 3I Atlas has displayed non-gravitational acceleration. If it doesn't produce a massive gas cloud in the coming weeks, it too might earn the designation of dark comet. Or, as Loeb has suggested, we might need to consider that these objects are not comets at all. A spacecraft with a propulsion system would show non-gravitational acceleration without cometary evaporation. It would be classified as a dark comet by astronomers in the same way that a cave dweller might classify a cell phone as a rare rock. The terminology reflects our assumptions about what we're looking at, not necessarily the reality of what it is. The timing of 3I Atlas's perihelion passage adds another layer of intrigue. The object reached its closest point to the Sun just 8 days after solar conjunction, during a window when Earth's observatories were effectively blinded. Whether this confluence of orbital coincidences is a signature of design or pure chance remains an open question, but it offers what Loeb calls a remarkable opportunity. The fact that 3A Atlas was hidden from Earth during its most critical phase means that any maneuvers, any transmissions, any unusual behaviour that occurred at perihelion happened out of our direct line of sight. We're relying on secondary observations from solar monitoring spacecraft, platforms that weren't designed for this kind of detailed analysis. The object also crossed the ecliptic plane on October 3, 2025, passing within tens of millions of kilometres of Mars. That's another coincidence worth noting. 3I Atlas's trajectory is aligned to within 5 degrees of the ecliptic plane, the disk containing the orbits of the solar system's planets. For an object arriving from interstellar space, where trajectories are randomly distributed across the celestial sphere, this alignment has a statistical likelihood of only about 0.2%. Add in the fact that it reached perihelion during solar conjunction, and the odds of all these factors aligning by pure chance drop even further. There's a concept in spacecraft mission design called the Oberth effect. It's a powered maneuver in which a spacecraft falls under the influence of a massive object's gravity, and then uses its own propulsion to achieve additional acceleration during the closest approach. The result is that the spacecraft gains more kinetic energy than it would by firing its engines in open space. The Sun's gravity well is the deepest in the solar system, making perihelion the ideal moment for maximum efficiency trajectory modifications. If 3I Atlas is a probe, if it's designed to use the Sun as a gravitational slingshot while also applying thrust, then perihelion would be exactly when you'd expect to see non-gravitational acceleration. Theoretical physicist Michio Kaku raised this possibility in a televised interview just before perihelion, suggesting that if 3I Atlas displayed an energy boost near the Sun, it could be evidence of the Oberth effect in action. The anomalies keep piling up. The blue colour at perihelion is the 9th documented oddity in 3I Atlas's behaviour, joining a list that includes its ecliptic alignment, its anomalously large mass, its sunward anti-tail observed in July and August, its unusually high degree of negative polarisation, its detection of nickel without iron, similar to industrially manufactured alloys, its faster velocity than previous interstellar visitors, its lack of detectable non-gravitational acceleration during the 5 months prior to perihelion, despite measurable mass loss, and now its confirmed acceleration at perihelion combined with its unprecedented blue appearance. Each anomaly on its own might be explained away. Taken together, they form a pattern that challenges conventional interpretation. Avi Loeb has developed what he calls the Loeb scale, a ranking system for assessing the technological likelihood of interstellar objects. The scale runs from 0, indicating a definitely natural object, to 10, indicating a definitely technological object. He ranks 3I Atlas at 4, not alarming but worthy of close scrutiny. It's high enough to justify serious investigation, but low enough to acknowledge that natural explanations remain plausible. The scale isn't meant to be definitive. It's a framework for thinking about the evidence systematically, for weighing competing hypotheses without dismissing either prematurely. NASA has been cautious in its public statements. Acting Administrator Sean Duffy, responding to a question about 3I Atlas on social media, stated plainly that this is the 3rd interstellar comet to pass through our solar system. No aliens, no threat to life here on Earth. That's the official position, and it's one shared by most astronomers. Megan Schwamm, a professor of planetary science at Queen's University Belfast, told reporters that the acceleration is consistent with increased sublimation of volatile ices, a phenomenon seen in both long-period and short-period comets. If there's an increase in the rate of volatile ices sublimating off the surface, she explained, then the comet would be observed to be speeding up. This happened with Oumuamua. It's not unprecedented. But Loeb pushes back against this framing. In his view, the burden of proof isn't on those proposing alternative explanations. It's on everyone to follow the data wherever it leads. He points out that comet experts have a tendency to define comets by their tails, and then, when an object doesn't show a tail, to invent terms like dark comet to preserve the cometary classification. It's circular reasoning. If the tail is what makes a comet, then an object without a tail shouldn't be called a comet at all. It should be called something else. And if that something else displays non-gravitational acceleration without mass loss, then technological propulsion becomes a valid hypothesis, not because it's likely, but because it's consistent with the observed data. The European Space Agency's JUICE spacecraft, currently on its way to Jupiter, passed within 64 million kilometres of 3I Atlas on November 4, 2025. Its instruments, including the Janus Visible Imager, the Magis Infrared Spectrometer, and the SWI Submillimeter Wave Instrument, were in a position to gather post-perihelion data unavailable from Earth. Those observations, combined with continued monitoring from NASA's Juno spacecraft and Mars orbiters, will provide critical information about the object's state after its solar encounter. Did it fragment under thermal stress, as natural comets sometimes do? Did its brightness remain elevated, or did it fade? Did the expected gas cloud appear, or is the object still showing anomalous behaviour without the cometary signature? December 19, 2025 is the date marked on every astronomer's calendar. That's when 3I Atlas makes its closest approach to Earth, passing at a distance of 269 million kilometres, roughly 167 million miles. It won't be close enough to pose any danger, but it will be close enough for detailed observation. Hundreds of ground-based telescopes will be trained on it. Hubble will perform ultraviolet spectroscopy to determine the composition of its gas emissions and measure its sulfur-to-oxygen ratio. Webb will conduct near-infrared and mid-infrared observations to probe the object's thermal signature and chemical makeup. If there's a massive debris cloud, we'll see it. If the object is still anomalously blue, we'll measure it. If it maneuvers again, adjusting its trajectory in ways that gravity cannot explain, we'll know. The implications extend beyond this single object. 3I Atlas is the third confirmed interstellar visitor in less than a decade. The first, Oumuamua, arrived in 2017 and left behind more questions than answers. The second, 2I Borisov, discovered in 2019, behaved like a conventional comet, displaying a clear coma and tail, with chemical signatures matching expectations. Now we have 3 Atlas, which shares some features of both predecessors while introducing entirely new puzzles. The Vera C. Rubin Observatory in Chile, with its unprecedented wide-field survey capabilities, is expected to detect dozens of interstellar objects over the next decade. If even a fraction of them display the kinds of anomalies we're seeing with 3I Atlas and Oumuamua, we're going to need a better framework for understanding what we're looking at. Loeb has proposed the development of an alert system consisting of solar-orbiting telescopes and interceptor spacecraft, designed to study future interstellar visitors before they leave the solar system. The idea is straightforward. If we detect an object early enough while it's still inbound, we could launch a probe to rendezvous with it, take high-resolution images, measure its composition directly, and potentially even land on its surface. The technology exists. What's needed is the will to deploy it and the funding to make it happen. The Galileo project, which Loeb directs, is working to expand its capabilities, hiring new postdoctoral researchers to analyze incoming data and develop mission concepts for future encounters. The debate over 3I Atlas isn't going away. It's going to intensify. As more data comes in, as the December observations provide clearer answers about the gas cloud and the object's post-perihelion state, one side of the debate will gain ground. If the cloud is there, if it matches the mass loss predictions, then 3I Atlas is a comet, an extraordinary one, but ultimately a natural object. If the cloud isn't there, if the object remains anomalous, then the conversation shifts. Then we're no longer asking whether natural explanations are sufficient. We're asking what it means if they're not. Right now, in early November 2025, we're in the waiting period. 3I Atlas is re-emerging from behind the sun, becoming visible again in the pre-dawn sky. Observers around the world are starting to pick it up, tracking its position, measuring its brightness, looking for any signs of change. The data is coming in slowly, observation by observation, spectrum by spectrum. Each new measurement refines our understanding, narrowing the range of possibilities, bringing us closer to an answer. What makes this moment remarkable isn't just the science, it's the transparency. Unlike previous eras of astronomy, where discoveries were carefully controlled and released through official channels after months or years of peer review, we're watching this unfold in real time. Loeb publishes his analyses on Medium within hours of receiving data. Amateur astronomers share images and measurements through online forums. Independent researchers run their own calculations and post findings on social media. The process is messy, contentious, and sometimes chaotic, but it's also democratic. Anyone with access to a telescope and the relevant expertise can contribute to the conversation. Anyone with curiosity can follow along. The story of 3I Atlas is far from over. We're still in the middle chapters, still gathering evidence, still weighing competing interpretations. But October 29th, 2025, the day Davide Farnocchia filed his report confirming non-gravitational acceleration, will be remembered as a turning point. It's the day we stopped treating 3I Atlas as just another comet and started treating it as something that demands deeper investigation. Whether that investigation ultimately reveals a natural phenomenon we don't fully understand or something far more extraordinary, we're about to find out. The universe is vast and we've only just begun to explore it. Interstellar objects like 3I Atlas are messengers from distant star systems, carrying information about planetary formation, stellar evolution, and the distribution of matter across the galaxy. They're rare, fleeting, and precious. Every one we detect is an opportunity to learn something new, and if, just if, one of them turns out to be more than a rock or a snowball, if one of them carries signs of intelligence, of design, of purpose, then everything changes. We're no longer alone. We're no longer the only ones capable of reaching across the void. December will tell us more, the observations are coming, the data will speak, and whatever it says, we'll be listening. Because this is what science does. It follows the evidence, it asks hard questions, it challenges assumptions, and it doesn't stop until the answers emerge, no matter how strange, no matter how unexpected, no matter how world-changing they might be. If you've made it this far, thank you for joining us on this journey through one of the most fascinating astronomical events of our generation. Make sure to hit that like button if you found this deep dive valuable, and subscribe to Tales of Gravity for more in-depth coverage of 3I Atlas as the story continues to unfold. The universe doesn't wait for us to catch up, but together we can try to keep pace. Until next time, keep looking up.